Okay, so today we're going to be talking about inverse functions. This is chapter 5.2 in your book. Hopefully it's going to be a little bit shorter, but let's just get right into it. So first of all, we want to know what an inverse function actually is. Hopefully at this point, all of you know what a function is. If not, you really haven't been paying attention. Inverse is something that you've probably heard a lot. Hopefully you know what it means already, but if not, that's okay. So throughout math, you've used inverse operations all the time. For example, when we're solving the equation 3x plus 2 equals 11, there are two inverse operations you have to perform. First one, you have to subtract 2 from both sides. Subtraction is the inverse of addition. And then after that, you have to divide both sides by 3. Now, obviously, you can solve this really easily. You're going to get 9. You probably don't even have to think about it in this case. You might be able to do it in your head. Doesn't really matter either way. But the point is, the way to actually solve it out on pencil and paper, the official, or like I guess the right way, is to do these two inverse operations. Now, again, we don't really think about doing those. Those probably come naturally to everybody at this point, but they're basically undoing what you did initially to this x value, right? This is effectively telling you to multiply x by 3 and then add 2. And then what we're doing is we're taking 2 away and dividing it by 3. So we're doing the inverse. Inverse functions are effectively the same thing as inverse operations, but rather than doing undoing individual operations, so rather than like getting rid of this 2, right, they're undoing the entire function. The notation for an inverse function of f of x is f to the negative 1 of x. So the reason that I say specifically of f of x is if you have g of x, it's not going to be f negative 1 of x. It's going to be g negative 1 of x, right? So the inverse of that, if you had a function h of x, then the inverse is going to be h to the negative 1 of x. If you have this little negative 1 over your function, I guess, symbol letter, that means that it's the inverse. So first off, let's start helping, or it helps to think of inverses in terms of story problems to help conceptualize them a little bit. So let's think of some real world actions and see how we can visualize these. So for example, if we consider our initial function, putting on a coat and then heading outside, it's cold or whatever, it's the middle of winter in Oregon. So you're putting on something warm and then you're heading outside into the cold. Right? We can easily find the inverse of that. In this case, that's going to be entering the house and then taking off the coat, right? You've undone the actions that you do. Now, this is obviously not a one-to-one comparison of mathematical functions, right? Like if you wanted to make a box of macaroni and cheese, for instance, you can't unboil water to undo that. You can't unmix the cheese and stuff. You definitely don't want to undo the part after you eat it. So, it won't work necessarily for everything in real life, but there are some basic inverses that we can kind of conceive of. Now, mathematical functions as stories, we can, specifically the book likes to do this a lot. I'm never a huge fan of it, but some people, I guess it helps make this easier. So let's say a function told you to take x, add 3, and then multiply the result by 4. Now, we could write this out mathematically, and I'm going to do that in just a second. But for right now, we want to find the inverse without bothering to do any fancy math stuff. So we have our x value. This is our start. We're going to add 3, that's our first operation, and then we're going to multiply the result by 4. So to undo that, we're going to take our starting number, we're going to divide it by 4, and then we're going to subtract 3. Now, you'll notice that we do the inverse operations and go in the reverse order. We started in the initial function with adding 3, and then we multiplied by 4. In our inverse function, we're dividing first, which undoes the multiplication, and then we're doing the subtraction, which undoes the addition. This makes sense conceptually if you think about like our coat example. Let's say you put on the coat because it was raining outside and you didn't want to get wet. If you're coming back in the house and you take the coat off first, which would be doing things in the same order, you're going to get all wet right before you go in the house. That doesn't really help you very much. So you want to come into the house first and then take the coat off. So we go in both the reverse order and we do the inverse operation. Now, we can also show that this is what you have to do mathematically. If we look at this, we have x plus 3, and then we multiply the result by 4. In order to show this mathematically, we have to put this in parentheses. Now, let's say x equals 2. So we're going to do 2 plus 3, g equals 5, and then we're going to multiply the result by 4. That gives us 20. Now, if we went in the same order doing our inverse operations, we'd have 20, we'd then subtract 3, because that's next in our initial. That gives us 17, and then we divide that by 4, and we end up with 4.25, which is not the x value we started with. However, if we do them in reverse order, we'd get 20 divided by 4, which gives us 5. Then we subtract 3, and that gives us 2, which is what we started with. So we need to do the inverse operations and go in the reverse order. Hopefully that makes some sense conceptually. Now, we can also look at inverse functions as graphs and as data tables. We're going to do both of those things before we get to the fancy math parts. So hopefully from earlier in the year, you remember the vertical line test. If we think of the function x squared, the vertical line test was used to determine whether or not this was a true function. If you could draw a vertical line through it at any point and it hit multiple times, so let's say I had a function or a graph that looked like this, then this would tell you that it is not a true function. You have to have one output for every input of x and no more than one. Now, we finally get to see the use of the horizontal line test. The way the horizontal line test works is if you can draw a horizontal line through a function and it hits at more than one point, so same thing as the vertical line test, then the function does not have a true inverse. Now, that probably sounds a little bit weird, and I'm going to paraphrase just a little bit. This is what your book says, but I want to be a little bit more clear. The inverse is not necessarily a function if you have the horizontal line test that passes it, and I'll show you that right here. So let's again look at the function of x squared. This isn't going to be exact because I'm not going to bother to draw it out all exact it's a little bit off. Now, obviously, vertical line test, we know this is going to pass. There's no point that it hits more than once. But horizontal line test, it very clearly fails. You might be thinking, why? This is x squared. The inverse of x squared is just the square root of x. Everybody already knows that. The problem is, if you graph the square root of x, that part's not too hard. It looks something like this. Again, the numbers are smaller. I'm not doing the exact ratio. This is what it looks like. But there's a problem. You'll see that this one has negative numbers. I can't take the square root of -3 and put it on a real graph because the square root of -3 is equal to some weird number times I, right? When we have the square root of a negative number, we have to use I, and that doesn't exist on a normal graph. So that's why we say that this does not have a true inverse function, right? No matter what I do, I can't take the inverse of -9, or the square root of -9 on a graph. Now, I can do it mathematically, but again, it won't be a function, right? The other way you could potentially do this is you could say, well, the square root of 4, for instance, is both 2 and -2. So let's put this in the right spot. Right, so I can just draw it like this. Well, now this is once again not a true function because it doesn't pass the vertical line test. Right, there are multiple outputs for single inputs. So that's a bit of an issue as well. Now, the other thing that the horizontal line test does, I want to mention two other things. So first, let's look at, again, this is an approximation, but let's look at the graph of x cubed. So you'll notice that this actually does pass the horizontal line test, ignoring my really bad line right here. Ignore this whole section. But this will pass the horizontal line test everywhere. You might be thinking, wait, how can x squared fail the horizontal line test? So no true inverse, but x cubed has a true inverse. That doesn't make any sense, right? The reason for that is actually this. So if we take the square root of x, x cannot be negative. Right? It doesn't work. We can't take the square root of a negative number and plot it somewhere on a graph. However, the inverse of a cube is obviously a cube root. And if the cube root of x is negative, oops, that's just fine. We can do that all we want. Let's look at the cube root of, let's say, -8. Right? If you plug this into a calculator, or if you just know it off the top of your head, you're going to get -2. The reason is -2 times -2 times -2. The first two negatives cancel each other out, so you get a +4, right? So when we square it, we're going to get 4. But when we multiply it by -2 again, we're back to this -8, which means that we can have a continuous function that goes both positive and negative with the cube root. So cube roots don't run into imaginary numbers. This is actually true for all odd functions. So x to the 5th, x to the 7th, etc., etc. All of those can have inverse functions, unless you do this. If I do x cubed plus x squared, right? And you could do plus x plus 3. Doesn't really matter. This, once again, can't be truly inverted. You can't take the square root of a number, of a negative number. So this function right here does not have a true inverse. If we get rid of this, though, it could. I don't necessarily know off the top of my head whether or not this one specifically does. Some of them change. We don't need to go into that. But basically, you can graph it, do the horizontal line test, and it'll tell you. This is just a warning that if you see an odd function, it may, in fact, have an inverse that is actually a true function. So don't rule them out just because you see an exponent on your x, is the point I'm trying to make there. Now, the last thing I want to look at is how you can actually calculate an inverse function, or how you can calculate the result of an inverse function based on its graph here. So if this is f of x, this line, then we can calculate, for instance, f of, let's say, 2. Right? That's not too hard. We go to x equals 2. It's right here. That equals 0. Now, another thing we can do is calculate the inverse. And the way we do that is by switching our y and our x value. So for instance, if I wanted to find f to the -1 of, let's say, 3, then what I'm going to do is, instead of going to x equals 3, I'm going to go to y equals 3. So we're going to go up here. We're going to find the x value. That looks like it's at 5. My f of x is kind of in the way. The answer is 5. Now, that might seem a little bit weird, but let's look at a couple other ones just in case. So let's do f to the -1 of, let's say, -2. So we go to -2. Oh, that's 0. Okay, easy enough. And then let's do f to the -1 of, let's say, how about 1? Go somewhere in the middle. We go up to 1, come over here, that's at 3. So we have all these values for this inverse function that we found from this graph. Now, we could calculate this out. I already know what the slope of this line is. It's actually this line right here, f of x is equal to x minus 2. The y-intercept is at -2. The slope is 1. You can see it's going up by 1 every time we go up by 1, so that one's pretty simple. This means that the inverse function, f -1 x, is just the inverse of this, right? It's x plus 2. You'll notice that all of these values, if we add 2 to 3, we get 5. If we add 2 to -2, we get 0. If we add 2 to 1, we get 3. We've already calculated all of those just by using the inverse. So that's one of the cool things about inverse functions, is with the graph of a normal function, f of x, you can find the inverse of specific numbers, right? So I can go to whatever I want on the y-axis to find the inverse of, or the result of the inverse function of that number. Looking at tables. So if we use specific values, we can see a very specific relationship between functions and their inverse. In general, if f of a equals b, then the inverse function of b equals a. Now, that probably sounds more complicated than even the last slide, which already is probably confusing. But when we look at some examples, it'll make more sense. So in this case, we have some function f of x that gives us 12 when we have x equals 1. 7 when x equals 2, 3 when x equals, or 5 when x equals 3, 2 when x equals 4, and 3 when x equals 5. This isn't a real function. I mean, it might be a real function, but that part doesn't really matter. What does matter is this. Since we have this table, we can just take the inverse, right? By definition, if a normal function gives us a result based on an x, then using that same result as our x value in our inverse function should take us back to our original. So if x equals 1, if when x equals 1, f of x equals 12, then when x equals 12, the inverse of f of x equals 1. Right, so all these numbers are just flipped, which is kind of an easy, quick, cool way to establish this relationship right here. So if you ever make data tables, I wouldn't recommend doing them this way. This isn't the fastest way, but if you're analyzing them, you can very quickly fill them in like this. That can be really helpful. But this is one way you can test whether or not something is an inverse function of the other. Now let's look at the important stuff. Symbolic ways of solving functions. Being able to do it graphically and numerically in tables is useful, but being able to do it symbolically is just going to be the fastest way to do them most of the time. You do have to be able to actually check to make sure that a function is one-to-one. So you have to be able to conduct that horizontal line test or some other way of making sure that you don't get multiple outputs for the same input to determine that f of, or inverse function, so f to the negative 1 of x, is actually a function. You can do this by solving for f to the negative 1 of x and then plugging in a bunch of different values and testing them to see whether or not you get multiple outputs for the same input. But that's not necessarily going to be something that, or multiple inputs resulting in the same output. But that's not necessarily that big a deal. So then we want to revert, right. So in order to solve for the inverse function of a given function, so first of all, you need a given function to be able to solve the inverse, but we must first make sure that f to the negative 1 of x is actually a function. Then what we want to do is revert to old algebra for a minute. Now, what does that mean? That means we're going to take our f of x equals whatever and replace it with a y. Right? A lot of you were asking at the beginning of the year why we're doing this f of x notation. We talked about that in the last chapter. We started doing f of g of x and things like that. But now for inverse functions, it's actually more useful to have this right here, the y equals 3x plus 2. And the reason for that is, what we're going to do next is switch x and y. So basically take y, plug it in wherever you see x, and take x and plug it in the one spot you're going to see y. So that'll go to this, and then we solve it for a new function. So in this case, right, we already know right away that the inverse of this function is going to be x minus 2 divided by 3, right? We have, we're multiplying by 3 and then adding 2. So our inverse is going to be subtract 2 and then divide by 3. That makes some basic sense. What we can do is we can actually solve for it algebraically, though. This one's obviously is a very simple function, so taking the inverse isn't very difficult. But to prove that it's helpful to prove that this is how you can solve for it mathematically. So in this case, if we want to solve this for y, we're first going to subtract 2. So we have x minus 2 equals 3y, and then we need to divide both sides by 3. And what do you know? That's exactly what we have right up there. So y equals x minus 2 over 3. Okay, let's look at a couple of example problems and then we can move on. Now, first and foremost, I would recommend graphing these. You don't necessarily have to graph them, but we can go ahead and solve them first anyway, and then I will show you why this doesn't exactly work. So this one we know just because it's got an x squared in here, and I already told you that this won't have a true function as its inverse. We already know that f of negative 1 or f negative 1 of x will not be a true function, but we can still solve for it algebraically. So first thing we want to do, y equals 3x squared plus 6x plus 3. Then we need to do x equals 3y squared plus 6y plus 3. Now, here's where we're going to get into a bit of an issue. We need to find some way to factor this out so that we can actually solve both sides. And this is a really tough operation to undo, but we should be able to find a way to do it. So first of all, we can divide everything by 3. That's going to be helpful because it's going to factor out, or I guess we can factor out a 3 from this equation. That's going to give us x over 3 equals y squared plus 2y plus 1. Now, in this case, this actually factors to x plus 1 squared. Or I guess y plus 1 squared equals x. Now, here's where this becomes a problem, or I guess x over 3. We take the square root of both sides to get rid of this. These will cancel. We're left with the square root of x over 3 equals y plus 1. So we get y equals square root x over 3 minus 1. Problem is, when you take a square root, as we've learned many a time from our quadratics unit, it's a plus or a minus. And when you have a plus or a minus, the square root right here, you're going to get some number, or you're going to get multiple numbers for any x that you put in here, right? So if I put in, let's say, 27, Right? 27 divided by 3 is 9. The square root of 9 is 3. I'm either going to have 3 minus 1 or negative 3 minus 1. That's going to give me either 2 or negative 4. That's two outputs for the same input, so this is not a true function. Now, we can go ahead and still put it in here. It is negative 1 plus or minus the square root of x over 3. But that's not a true function. So it's not necessarily going to be, graphing this will not be a particularly useful thing, or at least when you graph it, you're going to get some weird thing that looks something like this. So you'll have, vertical line tests that you'll fail all over the place, and it won't be a real function. Now this one is a little bit easier. We turn this into y equals 2x cubed plus 3. Then we turn that into x equals 2y cubed plus 3. Solving this isn't too bad. We subtract 3 from both sides. Whoa, don't know what I did there. Sorry. Okay, well, it's going to look like this for the rest of the class, I guess. Well, that's kind of cool, actually. Yeah, anyway, so we subtract 3 from both sides. We get x minus 3 equals 2y cubed. That's so cool. Then we need to divide both sides by 2. So we get x minus 3 over 2 equals y cubed. And then we can just take the cube root of both sides. So we get y equals the cube root of x minus 3 over 2, or g to the negative 1 of x equals the cube root of x minus 3 over 2. Right, like this. This one, you can graph it to make sure that this is a real function, but it should in fact be a real function. So hopefully that's not as complicated as I think it sounds like it was. The homework for this one won't be too terribly bad. We'll go over some of this stuff in class a little bit, I think, as a group, because I think that'll be useful. But otherwise, you guys are done for today.